let us now describe the Turing machine, which will perform this conversion of a unary representation of a number to its binary representation according to the strategy which we had outlined. So, as an example, think of this string of ones, which is of course 5 in unary, and we would like to convert it to binary. Remember that we will use for binary representation the symbols A and B, where A would stand for 0 of the normal binary representation and B will stand for 1. So, this is 5 and therefore, what we should get here B A B, which is 101, which is the binary representation of this unary number. What we will do is, we have the convention that our Turing machine will start at the leftmost one of this input string. So, the Turing machine will start here scanning this particular symbol. So, let us see how we can carry out the strategy by means of a Turing machine. So, let us say this is the initial state, and in this initial state it is scanning this leftmost one. Now, we said that as soon as this machine sees this one, it will convert to an X. This one, it converts to an X, and what should it do? It should move to the right, skipping the next one, etc. So, therefore, this is a right moving state, it comes to, and in this, when it sees a 1, what should it do? It should just go back to this state, so that it can cross off the next one. So, and as it, so remember that initially it was here. So, this was converted to X, right, and the machine came here, and in this, when it sees a 1, it just skips that 1. So, this 1 is written as 1 and it moves to this state, and in this state it should be scanning this particular symbol. So, therefore, now we know that this is also a right moving state. So, this 1 is left as 1. In this state, now it is scanning this particular symbol, which will be converted to X. It comes here, and in this state it is now seeing this 1, which will remain as 1, because 1 is not being changed. So, 1 is being overwritten by 1 itself, and then it moves to the right. Therefore, the head will be here scanning this 1, but this particular 1 will be converted to X, right, and it comes here having converted to X, right, and then since it is a right moving state, the head will be under this blank. But what does now seeing a blank mean? It means that the input is entirely scanned in this pass, and also see what has happened is this one was crossed and you found a 1 corresponding to this one was crossed, you found a 1 corresponding to this one was crossed, and you did not find a 1 corresponding to this particular one which was here. So, that means this original length of the string is odd, and therefore, it should print B to the first blank cell available. So, therefore, it keeps on now moving to the left, right, and in this, as it moves to the left, it just keeps on moving to the left, keeps on moving to the left. When it reaches a blank symbol here, it will convert it to B. Why B? Because it knew that the string of ones that it had considered in this pass is odd, and the remainder by division with 2 is 1, and therefore, our code of 1 being B, it should print that B, and so it is here. So, therefore, having written this blank by B, so the situation will be like this. What should it do? Now, it should again start this process all over again on the remaining ones. Which are the remaining ones? The ones which is the quotient of division by 2. And that is indeed, see, 5 when you divide by 2, the quotient is 2, and that is what you have here. There are 2 ones, right. So, it will come here, and then having written B, it should go over this side. So, therefore, it is a right moving state, and in this, as it moves to the right, it ignores this cross, it sees a 1, and this one, it is converted to x, and this process begins again. Okay. So, now let us go over again. So, this 1 is now changed to x. Having changed to x, the machine is in this state. This sees an x, whatever self loops we are not writing, that means it remains there without changing the symbol. So, this x it skips. This one takes the machine to the top state without converting that 1 into anything, that 1 remains as 1. So, this one is here, and this comes here in this right moving state, and now it will again keep moving to the right, sees an x which of course it ignores. Now, it sees a blank. The head will be here in this state, and blank means again that the current ones we have already taken care of, and in this case, you see what had happened was, in this iteration what had happened, this one we converted to x, this one we could match it off to this, and which remained 1, and now it is here seeing a blank, which means that the number of ones in this part left was even. So, it now should print a, and therefore, it is similar to this, except in this part what it remembers is that it should print an a whenever it sees a blank. So, in corresponding to this, there is a left moving state, and so this is actually, as it is from here, it is moving to the right, and when it keeps on moving to the left till it finds a blank, which it changes to a. Okay. So, let us go over it again. What is going to happen? This, it will keep on after seeing this blank, it would have come to this state, and it will start moving to the left, it will skip all ones, all x's, this b, and when it sees this blank, it will change it to a, and then moves to the right. In this right, what it should do? It will keep on going to the right till it sees this one. So, these things do not change. This one is converted to x, blank. Now, it sees, so it is here, right, and what it finds? That it has reached a blank. So, on blank in these cases it would go to the left, but now remembering the string of ones that it had considered in this iteration was odd, and therefore, a B needs to be printed. So, it will now again go over to the left, and here this blank will be converted in the next step to B. And as the machine converts the blank to B. So, where is this machine now? This machine was here, it converted this blank to B, and it is now in the right moving state, and it will now it is not going to see any more ones, because all the ones have been crossed off. So, it will keep on moving to the right, and what will happen? It is going to see a blank. The moment it sees a blank in this state, what does it mean? That means, that there was nothing more to do, because all the ones now have been converted to excess, and that is why you are not seeing any one in the current space on which you need to work. And since you found that all ones have been taken care of, therefore, the job of conversion is over. Okay. So, let us see this once more, and remember here we are talking of a Turing machine where we have used our old convention that any transition which is not shown means the machine remains in that particular state without changing the symbol. So, I wrote here blank, but more technically or to be consistent with what we are writing, I should have said blank is replaced by blank. So, let us go over once more very quickly this transition diagram. So, remember that the machine would start at the leftmost one of a block of ones which are flanked on both sides by blanks. The machine would start here, and in this state, why this is the state? How do we know from this transition diagram that this is the initial state? Because there is an arrow coming from nowhere into this state, which indicates that this is the state in which we start the operation. So, in this state, if you see a 1, you convert it to x, go to this right moving state, that means the machine moves to the right, and when it sees another 1, it does not bother to change it, because this is the one which corresponding to the one which you had crossed off. Right. So, 1 gets converted to x, next one is not converted to anything, it remains 1, but it means that we have corresponding to this one, we have found a 1. So, we are back in this particular state. So, this alternately, so this we know that given a block of 1s, what we are doing is we are putting it, crossing it to x. So, first one, next one we are leaving it as such, crossing it to 1, next one as such, crossing it to 1, leaving it as such. But now, when we see a blank, that means that input space is over, and depending on whether the machine is here or here, it knows whether the input space had ones whose length is either odd or even. In this case, it is even, in this case, it is odd. So, this is what is going on, and here those transitions which we have not shown. So, for example, in this, if there was an x, in this state if you see an x, what does it mean? It means the machine remains here and moves to the right. That is the convention we have made use of. Notice that in this machine we have made a transformation of unary to binary, and something again you do not know how it could have been done at all by finite state machine. So, this is something extra that we can see that Turing machines can do, which we could not do by finite state machines or by PDA. All right. We have seen now several, at least 2 examples of Turing machines, both doing fairly interesting tasks. The first example was checking whether a string of A's, B's and C's had equal number of A's, B's and C's. The second one was converting a unary representation number into its binary representation. But in this particular course of theory of computation, our focus is not so much computing functions, but our focus has been to recognize languages. How do we recognize languages, or what does it mean to say Turing machine recognizes a particular language? As we are now seeing several examples of Turing machines, now we know what are the components or what go to define a Turing machine. Like if you look at this Turing machine, first of all it has a finite number of states. So, we can say a Turing machine consists of Q, a finite set of states, then it uses tape alphabet. So, that is all this is the set of all symbols which can appear on a particular Turing machine tape. Now a subset of this sigma, which is a subset of this gamma, is the input alphabet. Then one particular symbol we made a special, and that was the blank symbol. So, you can say blank, which is an element of the tape symbol, but which was not in the input, is the blank symbol. And the importance of the blank symbol is that this is the symbol which most of the cells in a Turing machine tape will have. Then of course, we had a transition function, and this transition function in this example was graphically or pictorially represented. But what is a transition function for deterministic Turing machine? It takes a state and some symbol which appears on the tape. So, this is the present state and the symbol that is being scanned, and corresponding to which there will be a next state and the symbol that will overwrite and the move. So, therefore, transition function is a mapping which is from the set of states crossed with the set of tape symbols, and its range is, it means given a present state and the present symbol being scanned, this transition function should tell you what is the next state, and therefore, this component is Q, what is the symbol being written, therefore, this we write, and with what is the move. So, one of left or right. Then you have of course a special state which is the start state. So, Q0, which is an element of Q, is the start state of the Turing machine. And in the context of language recognition, we should have some final accepting states. So, some f which is a subset of q, the final accepting states. And in these states, once the machine, if the machine at all reaches one of these states, then the machine halts. That is the convention we have. So, final accepting states are all halting. So, if you specify all these, then you specify a particular Turing machine. Different Turing machines of course can have different q, gamma, sigma, blank symbol may be different, transition functions will be different, etc. However, notice that this is finite, this is also finite, this is also being a subset of gamma, this is finite, this is one particular symbol. This is a map from q cross gamma, both are finite. So, therefore, and it is a deterministic machine we have said. So, corresponding to each one there will be one such component, give one q, one symbol will tell me what is the next state, symbol being written, the direction of the move. So, point is even this is a finite function. So, everything here is finite. So, therefore, the description of a Turing machine, whether you use a diagram or whether you use these symbols and then elaborate each one separately, whatever it is, a Turing machine can be described finitely, and that is a very important point. A Turing machine has a finite description. Now, you must realize that this is what is expected. Why? Because what we are trying is, our overall motivation is to capture the intuitive notion of an algorithm by Turing machines. Now, there can of course be many infinitely many algorithms, there can be infinitely many Turing machines, that is fine, but an algorithm is a finite object, is not it? Supposing I code an algorithm in my favorite language, programming language, whether it is C or Java, then that is a text, and that text is something finite. So, my every program is a finite, I can think of a program as a finite text. So, it is something like a finite entity or an object. So, if I am saying that our algorithms can be captured by Turing machines, then to retain that correspondence, since algorithms are finite things or entities, Turing machines also must be finite entities. And indeed, these are, as you can see, a particular Turing machine is represented in terms of these things, and these are all finite things, and therefore, this particular Turing machine is also a finite entity. Now, let us consider what we mean by recognition, language recognition by deterministic Turing machine. And the notion we shall use here is the configuration of Turing machines. We have spoken of configuration at least several times before when we talked of PDA, for example. We had a notion of configuration, and configuration is kind of snapshot which tells me at what point the computing device is, and this snapshot should have enough information that from that point onwards, if I would like to carry out the computation by the computing device, the configuration should have all the information to tell me to how to carry out those further steps of the computation. Now, configuration of a Turing machine, at least one tape Turing machine, the kinds of Turing machines that we are talking of, should have then what? It must tell me what are the symbols which are there now on the input and their order in which they are there. That is, the configuration must have the tape contents, and it should also tell me the state of the machine, and it should tell me where the head of the Turing machine is positioned currently. So, again remember that configuration should give me a snapshot which has complete information about the current affairs of that running of a particular Turing machine. So, at any given time, a Turing machine tape has some symbols and the read write head is positioned to be reading a symbol on the tape, and the machine is in some state Q. The configuration of the Turing machine must consist of all this information. However, tape is an infinite thing, isn't it? We said it extends to infinity in both directions. Then how do I represent this infinite thing finitely? Fortunately, remember that if to begin with we had only finitely many symbols on the tape initially, and after a number of steps non-blank cells will still be finite, will be bounded, because why? Because you see it is like this. Let's suppose initially this much was the space of the tape which contained all the non-blank symbols, which you can imagine the input. And then the machine after n steps may have moved to all this area in n steps. It could have at best converted n more blank cells into non-blank to contain non-blank symbols. So, after n steps, the number of cells which would contain all the non-blank symbols will be the original ones plus n at most, that is the bound. So, in providing tape contents, we do not have to of course say give all the blank cells. All we do is, so let us take this picture and let us say I had here A blank, A B, A D blank, let us say A, and all these cells are blank. So, I would represent this situation by saying A blank, A B, A D, A, and that is all I will write, with the understanding all the symbols to the left of this and all the symbols to the right of this, all these symbols are blank, right. So, now the machine is scanning this particular B in state Q in this picture, right. A convenient way of writing all this in one single line is to do this. We will write A blank A, and here we write the state and then B A D. So, this is the way we will represent configuration. So, couple of things again to say here, that this is a string which will contain symbols from the tape alphabet, including blank, like here we have one blank. But the idea is the current tape contents is this, and everything to the right are blanks, everything to the left are blanks. And now you see there is a state symbol appearing. The idea is that the machine is in this particular state, scanning the symbol immediately to the right. So, it is scanning this B, all right. And if you notice that this very conveniently represents whatever information that particular picture had, all right. So, now what we can say that initially, we always say that initially the Turing machine is scanning the leftmost symbol of the input. That is the kind of convention we all have all the time. So, what is the initial configuration? Initial configuration will be the input, let us say x, some string, and the machine is going to be scanning the leftmost symbol of this input, and that situation is very conveniently represented by this configuration. And notice our so we are saying that the machine is in state Q0 scanning the leftmost symbol of x, which is our input. Now, let us elaborate it a little bit. So, let us say x is A, B, some y, and suppose our Turing machine is such that in Q0, if the input is symbol, or not the input symbol, the symbol which is being scanned is A, then it goes to the state P, writing B and moves to the right. So, therefore, what would happen? Initially, in picture we may write like this, these are all blanks, here A, then B, and then this whole thing is Y, and these are all blanks. Initially, the machine is here in state Q0, and this in one step, what will be the situation? Of course, these will be blanks, and this A is converted to B, so B, and of course, nothing else changes. So, this A has become B, there was a B here, so that B is here, and then the string Y, and then of course, blank and so on. And the head will be, since the move is to the right, the head will be here. So, in terms of configuration, what is the situation? Initially, my configuration was Q0 A B Y, and in one step the configuration became B P B P B Y, right. So, from this configuration we are getting this particular configuration. Why? Because the Turing machine had carried out one step of its activity. So, what we can see that if we consider that there is a space of configurations of a Turing machine, there is a relation amongst configuration. And what is that relation? Supposing there is configuration C1, another configuration C2, we say C1 derives C2 in one step, or C1 is related by this relation if the Turing machine in one step can go from C1 to C2. So, let us see, let us this way put it. We define C1, then this relation symbol to C2 if in a single step the Turing machine can go from configuration C1 to C2. So, therefore, this is a binary relation relating configurations, and of course, you can define another relation which we can say. So, if you remember, we are saying that this relation stands for machine. So, machine one step situation. In a single step from configuration C1, the machine goes to configuration C2. This we will say in 0 or more steps. One way of relating this to is that this particular relation, this is again a relation on configurations, and this particular relation is the reflexive and transitive closure of this relation. Even without going into those kinds of mathematical jargon, intuitively the idea is very simple. We will write C1 goes to C2, will express like this for a Turing machine M in case the configuration C1 from starting from configuration C1 in 0 or more steps you can go to the configuration C2. All right. Why are we doing all this? We are doing all this because very precisely we would like to capture the notion of accepting or recognizing a language by a Turing machine. We are trying to understand very formally and very rigorously what does it mean to say a Turing machine recognizes a language, and towards that we defined a relation on configurations, and this relation will relate two configurations provided from the first you can go to the second configuration in 0 or more steps using that Turing machine which you have in hand. So, to begin with, a Turing machine M, remember, it has a number of states. Its tape uses an alphabet which we are calling gamma. Let us say the input again is over an alphabet sigma, then it has a transition function delta, and it has an initial state Q0. There is a special symbol which is blank symbol, which let us write it as this, and then let us mention the states which are final accepting states. So, this is final accepting states. So, once more, this is the set of states of the Turing machine, this is the input alphabet or rather tape alphabet, this is the input alphabet, this is the transition function, the initial state, the special blank symbol, and the final accepting state. And LM is the language accepted by Turing machine M, this Turing machine. So, this stands for language accepted by m, and using our terminology now, we can very precisely say that this Lm is this set of all strings x over the alphabet input alphabet sigma, such that Q0 x, which is a configuration, which really stands for a configuration in which the every part of the tape is blank except where the input x is written. The machine is in its initial state Q0, scanning the leftmost symbol of the input, and from this configuration, if in 0 or more steps you can reach a configuration where some alpha is here and maybe p and beta, where p is an element of f. Okay. So, what we are saying is scanning the leftmost symbol of the input initially in state Q0, if in 0 or more steps the machine M, if it reaches a final accepting state, in that case the original x is in the language accepted by the Turing machine M. Right. Now, right away let me use another terminology. The set of all languages for which we have a Turing machine recognizer, Turing machine which can accept a language, such a language is called recursively enumerable language. So, let me, since this is an important concept, let me note it down. So, this is a definition. A language L is said to be recursively enumerable if there is a Turing machine M such that this language L is the language accepted by the Turing machine M. Right. So, recursively enumerable languages are those languages which are accepted, or we also use the term recognized, accepted by Turing machines. And this is the class of languages which we will consider extensively in next classes, but we already know from the first example that the language of equal number of A's followed by equal number of B's and equal number of C's. It means this language is a recursively enumerable language. Because we gave a Turing machine which recognized precisely this language. So, therefore, this particular language which we know is not context free is a recursively enumerable language. So, our goal will be to study this class of recursively enumerable languages and see which all languages, at least intuitively, which all languages are recursively enumerable, and if there are languages which are not even recursively enumerable. That will be our concern. before we end, let me say that we do not always write this whole thing recursively enumerable languages, we just simply write RE. So, this is an abbreviation